This breadboard has an ATtiny 412 that's implementing a sort of nightlight. This phototransistor detects darkness, and when it does, this LED lights up. And I can show you that by covering the phototransistor to make it dark, and the LED lights. I take the cover off, and the LED goes off again. There's also a switch that I can use to turn the LED on regardless of the brightness state, so it doesn't matter, it just stays on. What's interesting is that the ATtiny can perform this nightlight function with no software other than software used for initialization. When initialization is complete, the core doesn't have to do anything, and the nightlight function continues. In fact, the core can be put into a low power mode, standby mode, and this function still works. And so on the setup here, you can see there's a blue LED, and when that blue LED is on, the core is awake. When the blue LED is off, the core is in standby mode. And you can watch the power consumption change on this multimeter over here. So when the system is asleep, as it should be in a second, the power consumption is 2.67 milliamps. When it's awake, the power consumption increases to 9.78 milliamps. And even when the system is in the sleeping state with the blue LED off, it continues to function. I'll demonstrate this by changing the state of the LED when the blue LED is off, in other words, when the system's sleeping. So now I'll wait for it to go off. And now I cover this, and the LED comes on. So it's still working even though the core is asleep. I'll do that again. So it's operating even when the core is asleep. So this video is about how that works. What software do you need to initialize the system into this state? And how do hardware blocks on the ATtiny help you achieve it? In particular, there's a hardware block called the Event System, which is used to, in effect, tie other hardware blocks together and allow them to interact with each other even without software interaction other than initialization. And in fact, they can do this even when the core is asleep or in standby state. Here's a schematic of what the system does. We have a switch that is debounced needlessly perfectly with an SR latch, but the ATtiny can do it, so why not? And we have the phototransistor feeding a comparator. The capacitor slows the phototransistor's response so it doesn't react to my blinking overhead LED lights. If either source is high, the nightlight LED lights. The impressive thing is that all of this is implemented by hardware, not software, in the ATtiny. The major resource that gets consumed on the ATtiny is pins. This system diagram shows that. We use every available pin on the ATtiny. You can pause and study the connections. This diagram shows how ATtiny hardware implements the nightlight function. I covered the CCL and AC comparator in previous videos. See links below. It's the event system that's new here. Its block diagram isn't very helpful. It's better to explain what the event system does. It provides event channels shown as purple arcs in this diagram. Each channel is configured to link an event generator with an event user. Event channel 0 links the state of an input pin to CCL let 0 input 0. This is a common usage because sometimes CCL inputs use inconvenient pins like the UPDI pin or are not pinned out at all. Event channel 5 links the AC comparator output to CCL let 1 input 1. Each port, like port A, contains an output pin called EVOut. It can be an event user. You could have a channel route the state of an input pin to this output pin. Then the output pin would automatically reflect the state of the input pin. Megatinycore contains an event system library. Let me show you how to find its documentation. This is the megatinycore GitHub site. Recall that megatinycore is the software package that provides Arduino support to the ATtiny Series 0, 1, and 2 parts. And it contains lots of documentation, often available with links from this top-level README. But to find the event library, we first click here, and then on Libraries, and then we see the event library here. That's the source code, and it has a README. So if you scroll down, we see lots of documentation about the event library. So you should take a look at this, and I won't try to go through all of it because you can read it. But you can see that the events are sometimes level or pulse-based, and often they sort of just do the right thing for the context you're in, so you don't always need to think about it too much. Sometimes they contain synchronizers and sometimes they don't. But most important are these generator and user tables. So one thing to know is that the event system on 0 and 1 series parts is a little more quirky than on 2 series parts. And so it's separately documented, and the event tables are not completely compatible. So it's difficult sometimes to have code that could work on both a series 1 and a series 2 part. My example has some conditional compilation to take care of that. But basically, this is the table of all of the possible generators that are available on all of the possible event channels, like event channel 0, event channel 1, and so on. So you just have to dig through this table to find an event channel that's suitable for your purpose. And if I keep going down, we'll find the 2 series table, and it's a lot cleaner actually, but it's similar in concept. So you just have to look through the various events that are available on different channels to act as generators. And then if you go further, you'll find the event user table, and that lists all of the possible event users. And so to understand how to apply these, it's actually best to look at the software. So let's do that next. And here's the software. As we scroll down, the first thing we see is the libraries that we're going to use. And so the ones that are new to this video are the ones for sleep and for the event handler. We've seen logic and comparator in previous videos. So here's a define that you have to set depending on whether you're using a series 1 part like the 412 or a series 2 part like the 3224. So right now it's set for the 412. And we have a couple of pin defines, but let's get down to setup. And so the first thing we see is that in order to sleep later on, you have to say what sleep mode you want to go into. And so I'm choosing standby, which is a fairly deep level of sleep. And then you have to call sleep enable, which doesn't put the core to sleep, it instead prepares it to. And so a later on call actually puts it to sleep. And now here we see the first of the events. And so this is the API that's new for this video. And you can see it's really quite easy to use. So I'm using an input pin as a generator, so I have to set it to an input, and I want it to be a pull up. But then really the key is just you set the generator and set the user, and then later on you start the event, as you'll see below. So I'm choosing as the generator pin PA3, and as the user CCL0, which really means LUT0, event A. So that makes event A available as an input to CCL0 LUT0, and we'll see it used below. In the second event, the generator names are not consistent for some reason between Series 1 and Series 2, so the conditional compilation takes care of that. But what this one's doing is connecting a LUT0 out to LUT1 in. And the reason for that is I can't use the CCL linking facility because on Series 2, it kind of links in the wrong direction for what I want to do. And on Series 1, there's an errata. But the event is a good workaround. And then here, event channel 3 has the same names on both series. And what I'm doing is connecting LUT1 out to the port A EVOut pin. And the reason I have to do that is that the LUT1 out pin is PA7, but that's also the positive input for the analog comparator. So I can't enable it as the output of a LUT. So I use the event to instead take that output to the EVOut pin. The event system is often used to solve problems like that. And this next one is only needed on Series 1, so event 4. And what I have observed is that things are just a lot more glitchy and sometimes hard to explain on Series 1 than Series 2. So on Series 1, I noticed that if I used CCL feedback, it just didn't work in my switch debouncer in LUT0. So I had to use an event instead, connecting the output of LUT0 to event B, making it available as an input to LUT0. But on Series 2, that's not necessary. The feedback worked as I expected. And then finally, we have event 5 here, which is connecting the output of the AC comparator to event B for CCL1. And then we come to the AC comparator. So we've seen this API in a previous video, but I'm using one new feature, and it's kind of an interesting one. This call right here makes available to software the configuration structure that the API uses before you call the init method. And so that allows you to tweak register settings in the API for the comparator in ways that the author of the library didn't anticipate. So it makes it flexible. So in particular, what you do is use this syntax here to set the run standby bit inside register control A of the AC comparator. And what that does is allows it to keep running in standby mode. So if it weren't for this feature allowing you to tweak the configuration structure, you'd have to do something different or maybe change the library. So this is a good feature of this particular library. And then we come to the configuration of let0. And we've seen the CCL API before, so I won't spend too much time on it. Notice the syntax here for selecting an event as an input. And the conditional compilation about whether I use feedback or not for the reason that I mentioned above. And then there's actually one more quirk about the Series 1 parts. And what I've noticed and can't explain is that the Series 1 parts don't always work in run standby unless their clock is used for something. So I'm initializing the synchronizer even though I don't necessarily need it. But that's a workaround for this behavior that I can't explain on Series 1. On Series 2, everything's fine. And then we have the configuration of let1. So nothing terribly new here, except I'm using 2 events as inputs. And then similar problem with the needing to use a feature that uses the clock source. And so anyway, after all of that, I've initialized logic 0 and logic 1. And so now it's time to start the events, and that's the API for that purpose. And now we come to something interesting. I can't use the CCL start method directly because it doesn't provide me a way to set the run standby bit. And so I had to write my own function for that, this logic start. And if I scroll up to the top of the file, we can find that right here. And so it's doing the same thing as the library function, except that it's enabling me to select run standby or not. And on Series 1, I need it. On Series 2, I don't. And I don't really know why that is. It's just another difference between Series 1 and Series 2 that's hard to explain. But as usual, it's Series 2 that behaves more reasonably. And now, while we're up here at the top of the file, notice that I have an interrupt service routine for the periodic interval timer. And it's this interrupt that's going to wake the part from sleep. So that's why I need this interrupt handler here. But then going back down to the bottom of setup, we'll find the code that actually starts the periodic interval timer, and that's right here. And I think we've seen something like that in a previous video also. I'll put a link to my ATtiny playlist below, actually, so you can find these videos. And what this is doing is causing an interrupt about every 4 seconds or so. Notice I'm using a 1 kilohertz clock in that cycle time. And so then the next thing we need to look at is how we sleep and wake. And that's done in the main loop. And in fact, that's the only thing that the main loop is doing. It's doing nothing related to the light function at all. That's all autonomous. But anyway, what this is doing is having alternating periods where it's a sleep period or not. And when it's a sleep period, it sets that blue LED low and then calls sleep CPU. This is the API function that actually puts the part into its sleep mode. And if it's not a sleep period, it sets the blue LED high so you can see it, and then changes the sleep period to be the opposite for the next time around. So anyway, that's the API for going to sleep and how I made it have alternating periods about 4 seconds long of being asleep and being awake that we saw right at the beginning of the video. That was a quick tour of the software, and I'll put a link to the GitHub below where you can see it and look at it in more detail at your leisure. We've seen how the ATtiny Event System ties together ATtiny hardware blocks and lets them operate independently from the core, even when the core is asleep. See below for links. I'll end this video here. Thanks for watching.